is on the screen, autoequivalences of derived categories of moduli spaces of sheaves on K3 surfaces. Nick, please.
Okay, well, thanks very much for the invitation. Rena and I have been trying to do this for what feels like years now, and every time something comes up, either a pandemic or who knows. So it's good to finally be with you. So if this is the M seminar, maybe I can assume that people are interested in derived categories and in autoequivalences of derived categories, but maybe just like
how did you derive it from the letter M?
Oh, Rena told me.
Well, it's her opinion, but in general, it's kind of not necessarily concentrated on derived categories, and I would say rather not concentrated on them. So you should not expect too much.
Okay. Yeah. No, I don't. I mean, yeah. Thank you. So maybe let's say if unexpected equivalences from the derived category of coherent sheaves on one variety to another variety, if these are interesting and they reflect some sort of secret stringy connection between these two spaces, then maybe unexpected autoequivalences sorry, I'm having a little trouble here, from the derived category of one variety to itself are also interesting. And there will be, and if that sort of very abstract motivation doesn't do it for you, there will be a stringy discussion later. So what do we know in general? So if the canonical bundle of X is positive or negative, then the automorphism group of the derived category is generated by automorphisms of the variety itself and tensoring with a line bundle and the homological shift to the left and right. And so there's sort of nothing unexpected. But if the canonical bundle of your variety is trivial, then there may be many more. I don't want to imply that there's a trichotomy, right? Like it could be that the canonical bundle is neither trivial, positive, nor negative. You could take, something positive this way, cross something negative that way, or fibrations. But this is a place to start. And so maybe what are the first examples of non-trivial autoequivalences of the derived category of a variety are the twist around so-called spherical objects. So this was written down by Seidel and Thomas in, I think, 2000. And sort of had been in the mirror symmetry air for a while before that. So if I'm given some object F, maybe a sheaf in the derived category of X whose self-Xed algebra is the cohomology of a sphere. So that's, you have C and then C. Then you can build an equivalence, the spherical twist around F, which goes from the derived category of X to itself. That is not coming from an automorphism of the variety, usually, or it's not one of the expected things. And maybe for examples, I could take X to be a Calabi-Yau threefold and I could take F to be skyscraper sheaf on some P1 where the normal bundle of the P1 inside of X is O minus 1 plus O minus 1. It's the center of an Atiyah flop. And then this spherical twist will actually be, maybe you know, when you have an Atiyah flop, you get an equivalence between X and its flop. And if you go there and back, then you don't get the identity, but you get this spherical twist. So that's already something interesting. Or we could take my spherical object to just be the trivial line bundle on X. Or maybe some other examples. Maybe X is a K3 surface. And again, F is the skyscraper sheaf on some P1. Or it could be the trivial line bundle, or it could be any rigid stable bundle. And in this case, in the case of K3 surfaces, this twist around F was first studied by Meachan. Then TF goes back to Meachan. Let me spell his name legibly. Under the name of reflection functor. In his Tata paper, where he's sort of building the foundations of moduli spaces of sheaves on K3 surfaces, he uses these functors all the time. He doesn't emphasize the fact that maybe he doesn't even know at that point that they're autoequivalences, but he uses them a lot. Maybe I'll skip the recipe for this twist around F, but let me say that.
Sorry, Nico, I have a couple of questions. First of all, what are your assumptions on X? Is it smooth projective, like in general?
Yeah, X is going to be a smooth projective variety, and I think just for simplicity in the talk, I do want to assume that the canonical bundle is true. So
thanks. And then in this K3 example and OP1 on it, do you want self-intersection of P1 to be -2?
Yes, you get that for free. So the normal bundle, maybe I'll put it in green. The normal bundle of P, not there. The normal bundle of the P1 in X is always O minus 2. Maybe I'll say that if F is O of P1, then this spherical twist around F, it categorifies the Picard-Lefschetz reflection, which is actually, let me not lie, let me put the -1 there that needs to be there. Sorry, was that all your questions, Rena, or were there?
Yes, thank you.
Yeah, okay.
Is it possible to just quickly describe what are the spherical twists are
Sure.
so different that from the standard one?
Yeah, so the twist around F of some G is you take X between from G to F, tensor with G, and you have some evaluation map going to F, and you take the cone on this.
Okay, thank you.
And why is it not one of the standard ones? Maybe the best way to say it is that you could take some sheaf and turn it into something that's neither not a sheaf nor a shifted sheaf, but actually really a complex. Or you could maybe take one sheaf and turn it into a sheaf shifted by some amount, and then another sheaf will be shifted by a different amount. Like these are all things that can happen.
Thank you.
Yeah, thanks. So this is, okay. Now there's a family version due to Paul Horja. And he calls them easy spherical objects. I'm just going to give one example. I'm going to take Z to be a K3 surface. I'm going to take X to be the Hilbert scheme of 2 points on the K3. And I'm going to take E to be the length 2 subschemes. This is supposed to be a psi in Hilb 2, where it's a fat point. Rather than it's not 2 distinct points. It's, if you like Hilbert schemes, it's the exceptional divisor of the Hilbert-Chow morphism. So let's have a picture. So here's your Hilbert scheme. Inside it, you have this E, this exceptional divisor. And, well, the E maps to C, which is the K3 surface. Here's X was the Hilbert scheme of 2 points. If I have a fat point, just remember where it was supported. And how many length 2 fat points can I have at that in one space? Well, it's all the tangent directions. So this thing is actually a P1 bundle. And well, here, and let's label everything. So let's say the inclusion of E into X, which was the Hilbert scheme, is I, and the projection, this P1 bundle. Sorry, am I writing too small? I can fix this. Onto Z, which was the K3 surface. I have a new pen now, so I can suddenly write small again, but maybe that's not good. And this setup satisfies for every pair of objects in the derived category of the K3 surface, X's on the Hilbert scheme between I lower star P upper star A and I lower star P upper star B is X's on S between A and B. I need to move that. Tensor the cohomology of S2. And so it's
so it's too small. What is S?
Oh, sorry, that's the K3. Thank you. That's what I called Z. Thank you. Right. So if you think of an in the last page, you can think of an object as just a functor from the derived category of a point to X, and then instead of saying X between the image of the only well, you had that before, right? That was the condition before, and now you have this condition, which is sort of a functorized version of that, if you like. And you can construct an equivalence from the derived category of the Hilbert scheme to itself, which sort of, for things supported away from E, it's going to just be the identity, but for things supported on E, it's going to be interesting. It's the identity for objects supported away from E, but it's interesting on E. Maybe I should say you should think of this as very much a family version of having one P1 in a surface. Now we have a surface worth of P1s in a fourfold. So it's some family version. I want to talk for a minute about how How's my time? Well, my time's okay. I want to talk about the mirror symmetry picture and then come back to talking about autoequivalences and Rena and Timothy's work. So maybe here's a mirror symmetry picture. These autoequivalences of derived categories come from monodromy in the stringy Kähler moduli space. Or if you prefer, the space of stability conditions. It's not exactly the same thing, but it's related. Or the complex moduli space of the mirror. And right, so I've got, I want to take this not as mathematics. I leave it to other people to try to mathematicize this. I want to take it as motivation. So here's your Kähler moduli space. So you're moving around in this moduli space, you're fixing your complex structure, varying your complexified Kähler form. So the derived category of coherent sheaves is not changing, but the Fukaya category is changing, or if you go to the mirror, then the opposite is true. So maybe somewhere in the Kähler moduli space, there's some point, some singularity. At this point, E is contracted. Right? This exceptional divisor inside of our fourfold is contracted down to the surface Z. Right? So algebraic geometers tend to think of blowing up and blowing down as a continuous as a discrete operation, but symplectic people and string theorists think of it as a continuous operation because you're varying your Kähler form and the volume of that E or of those fibers, their volume is going to 0, and then in the limit, they're gone. And so there's some singularity of the stringy picture there, but as the monodromy around this point, the monodromy is, sorry, that green is totally unreadable, isn't it? Acts on the derived category of X as the spherical twist around I lower star, P upper star. And maybe there's some other point because, right, back up here, we were contracting a P1 in a Calabi-Yau threefold or a P1 in a K3 surface, but we also had like the spherical twist around the trivial line bundle OX. And that corresponds to over here, they call this the large complex structure, or sorry, the large volume limit. And here the monodromy is this spherical twist around O. Well, that's true for Calabi-Yau threefolds. I guess in this Hilbert scheme example, O is not a spherical object, but a P2 object, which I'll come to later. But again, I don't want to, maybe you want to mathematicize
Sorry,
this,
Nick.
and I invite you to do it, but I don't want to.
Can I
Sorry,
ask a
was there a
stupid
question?
Yes. So this is a very nice picture for a very special class of sort of spherical objects or spherical fibrations. Where would a random sort of ugly complex, which just has the right homological properties to be spherical, fit into all this?
Yeah, no, I agree. Well, here, let me try to say something about that. So when your Calabi-Yau, maybe X is a complete intersection in a toric variety, say high Picard rank, then we have a picture, like a nice toric picture of the Kähler moduli space. From Witten and on the mathematical side, Badarev and Borisov. And you look for singular points like this, like this blue one that I've drawn and this green one, where some aspect of their recipe blows up, and then you go back and sort of stare at the geometry and guess how to construct autoequivalence of the derived category of X. And at that point, you're doing mathematics again, right? Now, Timothy's question of if I have some random autoequivalence, could it have a geometric origin like this coming from subvariety being contracted? Yeah, this is a hard question.
Twist.
Yeah.
A random spherical twist. I was just wondering that does this picture mean that spherical objects which are not geometrical are somehow sort of DG deformations of geometrical ones?
Yeah. Should they be coming from?
Yeah. Should they be coming from one
some
of the
geometric place? I mean, it's a beautiful dream, right? And actually, in the main example that I'm here to talk about, it's going to turn out to be true.
Oh, good.
So I wouldn't like to let's fantasize, right? That every spherical twist is a deformation of compositions of ones that have some geometric origin. Right? That's a beautiful dream. We're never going to prove that, but we'll see an example of it that I think will make you happy. So let me come back to, especially since Timothy and Rena are here. Let me take this statement. Oop, I didn't mean to delete it. So earlier, we had this, and I could let f be the functor I lower star p upper star going from the derived category of the K3 surface to the derived category of the Hilbert scheme, and let R be its right adjoint then the statement above it follows from, or well, I don't know if it's actually equivalent, but they're both true and they're related. From showing that if I take R composed with F, that's the identity on the K3 surface plus shifting by -2, or if you like, it's the identity tensored with the cohomology like of a sphere. And now there's a huge generalization due to Ruquier, Ano, Logvinenko. We could put other names here. For any functor, maybe a Fourier, functor from the derived category of maybe one variety to another. You have the unit of the adjunction from 1 to R composed with F, and then you have some cone here if you work in either in a DG enough setting or if you work with Fourier-Mukai kernels. And if this is an equivalence, and another technical condition comparing the left and right adjoints, which sort of in Calabi-Yau settings tends to come for free. Then we can construct. I'll come back. and autoequivalence of the derived category of X. And in our example, I should say, for this Horja example, this cone is just the shift by -2. So that's definitely an equivalence. I might as well write the formula because as the cone of, you compose them the other way to the identity on X. Maybe you've heard a lot about this story because your colleague has worked on it, and her collaborator who's also here. Sorry, I'm trying to figure out where I am in my notes. Right, so these are called spherical functors. Okay. We're still on track for time. So here's an observation. So maybe I'll say in 2011, 2010. Well, in 2010, I heard a talk by Timothy about these spherical functors. And I happened to have recently come across an example of one. And so I got excited about this subject. I noticed an example of these, which is of a spherical functor. Come back. If I take, let's see, let me get my notation right. Let's take F going from the derived category of the K3 surface to the derived category of the Hilbert scheme of 2 points on it. Not this geometric thing that we had before, right? Not this one, but instead it's going to be induced by the ideal sheaf of the universal subscheme in the K3 cross Hilb 2. And again, we have this condition either x'd on the Hilbert scheme between the functor of A and functor of B is x'd on the K3 surface between A and B tensor the cohomology of S2, or R composed with F is the identity plus shift by -2. And let's see, am I managing my pages all right? Not very well. And therefore, thanks to this work that Rena and Timothy and others had been doing, you get an autoequivalence of the derived category of this Hilbert scheme using this recipe above. And I should say the kernel that induces that autoequivalence is a rank 2 reflexive sheaf on the Hilbert scheme cross with itself. And it's previously studied by Markman in the context of whatever hyperkähler geometry he was doing. He has this paper on the Bogomolov form that involves this sheaf. So in particular, this functor, this autoequivalence, takes a skyscraper sheaf of a point to some rank 2 sheaf that's a vector bundle almost everywhere except at the point. So it's really not coming from like the automorphisms of the variety. It's not moving around the points or tensoring them with line bundles or shifting them. It's turning them into rank 2 sheaves. It's really something new. Maybe I should point out that maybe just a fun aside that David Plog, and I think it was Andreas Krug, in 14 noticed that my autoequivalence and the Horja one above satisfy a braid relation. So if you're interested in autoequivalences of derived categories that satisfy braid relations, maybe that makes you excited. More generally, for the same functor from the derived category of the K3 surface to the derived category of its Hilbert scheme of endpoints, R composed with F is not the identity tensor cohomology of S2, but tensor the cohomology of Pn minus 1. And of course, you notice that P1 is S2. Or if you prefer, if we go back to and look at these X groups for a minute here, right? X between F of A and F of B will be X of AB tensor the cohomology of Pn minus 1. And I could have said earlier, but somehow I'm only saying it now. Huybrechts and Thomas had studied objects F whose X algebra is the cohomology of Pn. They call them Pn objects. And constructed autoequivalences from them. Pardon me. Equivalences from them that were inspired by mirror symmetry. So they're mirror to a construction of Seidel in the Fukaya category. Right, so Seidel has some Dane twist around Lagrangian PNs, and he constructed some autoequivalence, and they sort of stared at this for a while and guessed what was the right thing to do in the derived category of coherent sheaves, and they wrote their paper. And so in my paper on Hilbert schemes, I defined a family version, which I called P-functors. So these P-functors and associated autoequivalences. And my definition was somewhat ad hoc. And Ano and Logvidenko have been developing this idea of P-functors more systematically and professionally for many years now. Maybe you've heard about it in this seminar from Rena and from Timothy. So I want to make, I don't know, maybe a pause for 1 second. I want to make two remarks about this Hilbert scheme example. So far the story is, I heard Timothy talk about these spherical functors. I noticed that I had one, and then we also dealt with higher dimensional Hilbert schemes and not just Hilbert 2. And we've compared this to this much more geometric story with the exceptional divisor of a Hilbert scheme. So maybe two remarks. At this point, first of all, the Horja example. Let me spell his name right. Horja example above. I mean, which was not Horja's only example, right? Like Horja did more than that, but the one that I've been talking about is about Hilbert schemes. in the sense that it holds for any surface. Whereas my example, my construction only works for K3 surfaces. So it's not really about Hilbert schemes, it's about moduli spaces of sheaves on K3 surfaces. So the conjecture was that for any moduli space of sheaves M of sheaves, and I only want stable sheaves. I don't want any state. I want M to be compact and smooth, so I only want stable sheaves on no semi-stables on a K3 surface. The functor from the derived category of the K3, I'll call it F, to the derived category of M, induced by the universal sheaf, if there is one. And if there's not one, then we should talk about twisted sheaves, and that's for the paper, not for the talk. Satisfies R composed with F is the identity tensor, the cohomology of Pn minus 1, where the dimension of the moduli space is 2n.
Sorry, Nick, this kind of assumes that it's split, right? Your conjecture.
Sorry?
Are you conjecturing that they're all split P-functors?
Yes.
Cool.
Yeah, they're sort of the simplest possible P-functor. So what was this? This should be like, again, I like to do the more down to earth thing. Maybe this is more fancy than I need to be. Oh, come on, give me gray. The X on the moduli space between f of A and f of B is X on the K3 surface between A and B, tensor the cohomology of P minus 1. Right, that's the down to earth statement that doesn't involve any left adjoint functors or right adjoints. So, and actually today I'm going to announce this for most moduli spaces of sheaves on K3 surfaces of Picard rank 1. My time's all right. But like, maybe why would this be hard to prove? Why would this conjecture be? So why is this hard for sheaves of rank, bigger than 1? Right? Sheaves of rank 1, that's just the Hilbert scheme. It's just in some guys. Sheaves of rank bigger than 2, why is this hard? You have to understand, question mark. You have to understand the wrong way slices of the universal sheaf. So what do I mean by that? On your K3, cross your moduli space, you have some, we're assuming we have a universal sheaf. If I slice it this way, then I get a bunch of sheaves on the K3 surface, which are the ones that the point of the moduli space parameterize it, right? You're happy with those. But if you slice it this way, then a point on the K3 surface is parameterizing a sheaf on the moduli space, which is kind of a strange thing to do. And you have to compute X between these. Now, if your moduli space is the Hilbert scheme, and your universal sheaf is the ideal sheaf of the universal subscheme, sort of everything is so explicit that you can really get your hands dirty and do these X calculations. But in general, sort of, you don't know anything about these wrong way slices, so it becomes hard. And then my second remark, is that the geometric meaning of my Hilbert scheme example is pretty obscure. So this comes back to Timothy's question about, you know, when you're doing mirror symmetry, maybe you collapse some subvariety and you do monodromy around in the Kähler moduli space, and you have some twist that's related to some Mukai flop or something. That's all like really nice. Here I'm just doing some huge X calculation between wrong way slices of this ideal sheaf, and sort of there's no geometry in it, or at least, right? Like here, you had like this coisotropic P1 bundle in your hyperkähler, and that gave you a P1 functor, a spherical, an S2 functor, right? For my PN functor, I would really like to see a coisotropic PN bundle somewhere, and not just some crazy X calculation. Okay. So I wasn't going to spend very much time on this, but since Timothy asks, and since I really like it, I'm going to spend a minute. In 2015, I and Will Donovan and Kieran Meachan, we studied, let me write in English here. Donovan and Meachan and I studied certain some moduli spaces of rank 0 sheaves on K3 surfaces. All right, so if you have a sheaf of rank 0, probably what's going to be interesting is here's your K3, and inside it you have some curve, and on top of that curve you have some line bundle, or if your curve is singular, maybe some torsion-free sheaf. And this functor from the derived category of the K3 surface to the derived category of the moduli space induced by the universal sheaf, this factors into, first you go to the derived category of the moduli space, but via some like I lower star, P upper star, where inside your moduli space, you have a Lagrangian Pn fibration. So you have a Pn, or sorry, a coisotropic. Pn fibration. Coisotropic for the holomorphic symplectic form on the moduli space, mapping down to your K3 surface. And so now here you're not surprised to hear that this is a P functor, because there's some geometric P, I guess I should say Pn minus 1, where n, again, 2n is the dimension of the moduli space. So that has really some geometric meaning. It's related to some Mukai flop. You're happy. And then here, well, M has another nice geometric structure, which is that it's an abelian fibration over Pn. It's fibered in the Jacobians of these curves. And so here you have some like Mukai and Arinkin equivalence from the derived category of the Jacobian of a curve to itself, but in a family. And okay, so if all the curves were smooth, then you just use Mukai's good old equivalence between the derived category of an abelian variety and its dual. When the singular curves come in, then you need Arinkin's work. And the last thing to say, I could talk about this for half an hour, but because there are a lot of details. But I should also say, right, so when this moduli space is birational to a Hilbert scheme, via the Mukai flop, you get a Namikawa. They get Namikawa and Kawamata give an equivalence from the derived category of M to the derived category of the Hilbert scheme. And sorry, maybe I should have said this I lower star P upper star is a Pn functor, and therefore you post-compose it with an equivalence, and you get another Pn functor. So the new autoequivalence is conjugate, all right, on the derived category of your moduli space, is conjugate to the old one on the derived category of the Hilbert scheme. So maybe the picture, so the picture that we see here is we take a P-functor of geometric origin coming from a coisotropic Pn-1 vibration in a Lagrangian, you know, one of these sort of things that could be contracted in the string theory picture. And then we get an autoequivalence of the derived category of M, and we conjugate to get an autoequivalence of the derived category of the Hilbert scheme. And then we deform, and when we would deform, we lose the geometric origin, right? The Pn vibration doesn't come along for the ride, but we keep the last autoequivalence, right? The conjugate one. So this is an interesting picture, right? You sort of take three equivalences of geometric origin, one from the P-functor, one from the abelian vibration, and one from the Mukai flop. You put them together in some interesting combination. Now you deform your Hilbert scheme in a direction where none of that geometry comes with you, but still the autoequivalence that you made does come. Okay, maybe I'll pause for a sec before I get to the newest shit in the last 10 minutes. Okay, so now here's the new work. And this is me and my PhD student, Andrew Wray, who graduated last year. So his thesis came out in 2020, and then he's gone to get a tech job, which is what he wanted. I mean, he could have gotten a good postdoc, I think, but that's what he wanted with his life. So I can't blame him, actually. And that includes sort of all the things I'm about to say about twistor lines and hyperholomorphic sheaves, but not the P-functor business. So my job is to make this into a joint paper with the P-functor business in it. So I'm hoping that the paper will be done this spring or so, but I'm sorry to be talking about work that's not on the archive yet. I know that's irritating. So maybe I should put it this way. Can the same strategy work for moduli spaces of, rather than rank 0 sheaves, how about of higher rank sheaves? So a result of O'Grady from the 90s tells you that every moduli space of sheaves where there are no semi-stables, the smooth ones, on a K3 surface can be deformed by deforming the surface, actually, to one that's birational to a Hilbert scheme. Right. So maybe maybe you could hope you take the autoequivalence on the Hilbert scheme, you hit it with some equivalence of derived categories coming from the birational map, and then you deform to the one that you want to know about. There are two problems.
What is n here? You have a discrete parameter on Hilb. What it's in the moduli?
Oh, and where n is like 2n is the dimension of the moduli space. Thank you. Right, so there are two problems. One is this birational map to the Hilbert scheme could be very complicated. Maybe so, well, I was going to say maybe so complicated that we don't know how to build the equivalence, but actually this year, or maybe a month ago, Dan Halpern-Leisner finally put out his paper where he tells you how to build the equivalence. But you still don't know how that equivalence interacts with the universal sheaf, whether it turns this one into that one. So that even if you look into the guts of Dan's paper, it's still too hard. The second problem is that deforming doesn't work very well. Well, being a P-functor is an open condition when you deform, but maybe I need to deform for a long time and take some limit and then do another birational map and then deform some more, right? There's the fact that being a P-functor is an open condition but not a closed condition really messes with that strategy. So instead, this is what we're going to do. So from now on, let my K3 surface, so let's take a K3 surface of Picard rank 1. Maybe the Picard group is Z times some ample class. Let's let M be the moduli space of sheaves of maybe some rank R, which is greater than or equal to 2. First trend class is some multiple of H, and C2 is whatever it needs to be. And I want to assume that the greatest common divisor of R and D is 1, so there are no properly semi-stable sheaves. And then I want to use this fact due to Yoshioka, and then there's a sort of a more streamlined presentation due to Perego and Rapagnetta, which is that there's some big T such that the spherical twist around O of minus T, acting from the K3 surface to itself, turns all such sheaves, stable sheaves, into stable vector bundles. Of some big rank. And in fact, we could work out what the rank is in terms of all those numbers, but let's not do it. And so we get an isomorphism from my moduli space to some other moduli space of vector bundles. And we can compare the universal sheaves really easily. And the functor from the derived category of the K3 to the derived category of M is a P-functor if and only if F prime from, if and only if F prime is. Maybe for Timothy and Rena's sake, I'll say that F prime is like F composed with the spherical twist around O minus T, or maybe it's inverse. And on one side, and then the isomorphism between the two moduli spaces on the other side. So like if you know the calculus of these functors, it's not at all hard. So now let me come to the punchline. So we know that the conjecture holds for Hilbert schemes, that this functor induced by the universal sheaf is a P-functor and therefore can be used to construct an autoequivalence. Let's do the twist around O minus T, and now it holds for some moduli space of high rank bundles. Actually, maybe I'll call this M double prime just to irritate you. And we want it.
Sorry, Nick, can I ask a stupid question?
Yes.
So your theorem tells you that if you do the spherical twist around O of minus T, you will sort of turn stable sheaves into stable vector bundles.
Yes.
Why do you get all stable vector bundles for that stability? I mean, which just seems
sort of because the second Chern class of them is as negative as it can be without making the, well, no, that's not the answer you want to hear. If I have O minus, here's the answer you want to hear.
Mm-hmm.
If I have some sheaf F, F is a bad choice. If I have some sheaf G in my first family,
Mm-hmm.
and now for some big T, G twisted by T will be generated by global sections. So you'll get a surjection like that.
Mm-hmm.
And then you'll take the kernel. And because G was torsion free, now this kernel is reflexive and you're on a smooth surface, so it's a vector bundle.
Yeah.
Maybe it's kind of surprising that you can have a moduli space where there are no, like, where all the sheaves are actually vector bundles.
But what surprises me is, why do you get all the vector bundles with given Mukai, all the stable vector bundles with given Mukai vector by this procedure? I mean, you've explained to me sort of why does a sheaf
well,
G
because like one reason is that the spherical twist is invertible, right? And it's giving you an isomorphism on like a component of the moduli space, and then you know that the components are connected. But like this fact that if G was stable, then this kernel is stable, like this is really painful.
Yeah. I know, that's why I asked.
This is where Yoshioka and these guys are working really hard. And oh, sorry, I need to wrap up. Maybe we can discuss this more after.
Yeah, sorry.
So I want the conjecture on this M, and that will be equivalent to the conjecture, let's see, of this moduli space of maybe low rank sheaves, of rank at least 2, but not very big. And that will, by the same argument, that holds if and only if the conjecture holds on this M prime of high rank vector bundles. And then the input, what we do is like you choose, given this rank in first Chern class and second Chern class, we sort of make some very careful choices so that I can get from there to there by a twistor line, maybe a twistor family. right, these are, I should say these are happening on different K3 surfaces. So this is on one K3, and this is on another one. A twistor family of K3 surfaces. So, you know, K3 surfaces are hyperkähler. They have these three complex structures that satisfy the quaternion relations. And so you can sort of rotate through the space of complex structures. And this is also gives a twistor family for the moduli spaces, which are high dimensional hyperkählers. And this is where you really need to be, this is where you need vector bundles everywhere so that you can use all sort of gauge theory stuff to turn this twistor, to show that this twistor family and that twistor family line up with each other. And then the X groups that we need to control, I said we need to control these X groups between wrong way slices of the universal bundle. These are constant in twistor families. By work of Verbitsky on hyperholomorphic sheaves, hyperholomorphic bundles. So if we controlled the X groups over here, and then we do this twistor family, then we still have control of them over here. In a general deformation, you don't have control, but in this particular deformation, you do. And so you get the conjecture in general over here. And I've gone 3 minutes long, so I think I want to stop here and take questions.
Yeah, thank you very much. So are there any questions? Actually, I have kind of a question which is perpendicular to your talk, but related to what you said at the very beginning. So if kind of your variety is kind of ample canonical shift, so then automorphisms of the derived categories are easy to describe. And for K3, what is known about?
Right, so for K3, do we have, well, we certainly have a conjectural complete picture that I think it should be generated by twists around spherical objects. Around spherical bundles, is that true? And Bayer and Bridgeland have proved something. Maybe it's just for Picard rank 1. Like, maybe Timothy or Rena can bail me out here. They've proved something that's, I think it's just for Picard rank 1 that what you want to be true is true, because you have a pretty complete picture, like you have a complete conjectural picture due to Bridgeland that it should be generated by the expected things and these spherical twists. I think they can prove it in one case, but
yeah, I think I don't know if there is a new result, but I think it's Picard rank 1.
Okay, so spherical twists around line bundles, and I don't know, whatever other spherical objects you might have. But I think hoping to describe the whole autoequivalence group of any Calabi-Yau variety, like any particular Calabi-Yau variety, besides maybe that one, is just out of reach. It's very hard.
Yeah, I mean, it's for a kind of arbitrarily chosen K3 maybe, but for example, if you look for, I don't know, like elliptically fibered, something which has a structure of integrable system, so it could be maybe easier. Yeah, but I don't know. And another question which is kind of completely out of your talk, you can kind of at the level of K theory, you have these spherical twists, you have sheaves, you have a phi and well group, and so on. What about categorification? Like, I mean, I do not follow that industry.
Yeah, I mean, these spherical twists give you very nice actions on K-theory and cohomology.
What about the other generators of Borchards generalized Kac-Mealy?
I'm not sure I can answer that. I mean, this is a nice question. I mean, I guess with K3 surfaces, you can say that every automorphism of the K theory does categorify to one of these spherical twists. But like for hypercalars, for example, or Calabi-Yau through, yeah, I don't know.
So it's kind of spherical twist. It's sort of kind of a wild group.
Yeah.
But there are others.
The P twists are less fun from this perspective because they act trivially on K theory. When the spherical twists act by reflections usually, and then the P1 twist acts by the square of a reflection, which is nothing, and then the higher ones also don't do anything on K theory.
Well, usually at least we have spherical twists for the wild group and just tensoring with line bundles for the weight lattice or whatever lattice you want there.
Yeah, but it's again, it's sort of a fine wild group action, but I'm asking about the generators. You know, that's elements of the wild group do not belong to the enveloping algebra, so it's not kind of clear how to categorify the rest. At least I don't know, maybe experts.
I think Rina is really the person to ask about this more than me.
No, categorifying an algebra is a very tricky question in itself. So you usually have to adapt your definition somehow.
Yeah, I heard that answer, but all right. Okay, thank you.
I have heard no better answer. So
yeah, okay, thank you. More questions, please.
Maybe I could point out, like, if you wanted this to work for all K3 surfaces and not just Picard rank 1, the only obstruction is this result of Yoshioka. And it's very possible that somewhere in Yoshioka's oeuvre is exactly the fact that I want, and it's just a matter of finding it or asking him and hoping that he remembers everything he's ever written, which is usually a good bet for Yoshioka. So when we finish writing the paper, this may even improve, or maybe not. If we want to fantasize, well, maybe we should fantasize about the whole automorphism group of a hypercalar, that it's generated by automorphism, like autoequivalences coming from coisotropic PN bundles and from abelian fibrations and putting those together however you like, and then also deforming from one hypercalar to a nearby hypercalar with less geometric structure. That conjecture would be totally out of reach, but let's fantasize.
It's interesting. So you have coisotropic and you have Lagrangian, and basically it should generate everything. Yeah. Okay. Okay, more questions?
Yes, can I follow Jan's question? But a Alpha group, during the talk, I was thinking of the projective line. So first, that in that case, the derived category of the coherent sheaves is corresponding to the derived category of this chronicle quiver. And there is a called the BDP reflection functor that's kind of giving the autoequivalence of the derived category. So is this spherical twist is corresponding to that sort of autoequivalence?
For P1 spherical twists aren't relevant, but for its cotangent bundle they are.
Okay.
P1 is Fana, and he is talking more about Calabi-Yau.
So you take the cotangent bundle of the that's what I was trying to make sense of Jan's question. When you say you have in general you have a Alpha group, I can see that the non-bundles, when you tensor it, looks like with lattice you're doing the translation of the alpha group action, but the var group is coming from the spherical twists.
Right.
Am I right? And in this case, the variety should that what should be the underlying variety? Should be that be the flag variety or the cotangent bundle of the flag variety?
Well, again, I should let Rena address this because I'm not I'm not much of a geometric representation theorist, but sort of maybe whatever categorification you wanted to do with constructible sheaves on flag varieties, you should do with coherent sheaves on their cotangent bundles.
Okay, yeah. So that you already answered the question. Yeah. Thank you. Okay. So that's the principle, right?
That's certainly the philosophy. Is that Rena? Is that
okay? I see.
Yep, Nick, you're correct. This is how it works.
Okay, so because all what I was thinking, those were on the flag varieties, but in this case, that should be the cotangent bundle. Thank you.
By the way, I'm going to put these notes in the chat since.
Yeah, that's a good idea. Thank you.
Let's see. I'm saving this.
I forgot to remind. Okay. And while you are doing that, people are thinking about questions.
Wrong button. Okay, it should be there now.
All right. So those who are interested in downloading Nick's notes can try to do it. It's in the chat.
No.
So
all right, and if you wanted to put those on your webpage or whatever you want.
Yeah, and it works. I just tried. Yeah. Okay. Good. Okay. So last chance to ask a question.
Timothy, did you get your details?
Which details?
Well, I feel like I was in the middle of answering your question, and then I just...
No, that's fine. I mean, there are several issues there, but I think that it's should be reserved for when we have a nice blackboard, and I could ask you some specific questions about, for example, do you change the stability is defined by a line bundle. Do you change the stability criterion when you do this? How when you flip back, why does sort of applying the inverse of a spherical twist, why would it take sort of why would you be able to get you see, what confuses me is that you have I mean, you take your moduli space, which you want to turn into moduli space of high rank sheaves. Then you apply spherical twist. All right, you get a high rank sheaves, but why do you get all high rank sheaves in a certain moduli space? You said just apply the inverse of a spherical twist, but that is not guaranteed to land me back where I've started. It just gives me, something.
Yeah, I agree. It's not.
I'm just curious.
I agree. It's surprising that the inverse of the spherical twist would be in any way well behaved. I guess the point is you get doing one spherical twist, which you understand. Well, yeah. Maybe we can discuss it at a blackboard in 2023.
Yeah, or something.
Or by email or something.
Because once upon a time I was struggling with trying to check that the spherical twist preserves stability, and that was really hard. So
yeah, it's really bad. Like, you have to be Yoshioka to have the patience for this.
Indeed, indeed. So.
But the point is, you get a map from this moduli space to that moduli space. You know that they're the same dimension, and it's a bijection, and they're both connected. But if you wanted to show directly that the inverse map takes stable bundles to stable sheaves, this would be even worse.
Why don't you end up with something like double cover, or I mean, surely just the dimension doesn't sort of tell you that.
Oh yeah, wait. So you know that it's étale, and you know that it's a bijection. It's étale because it's preserving X1s, and it's a bijection.
Yeah, I guess that makes sense. Yeah.
And everything is simply connected, and yeah.
Yeah, sure.
So Okay.
Right,
All
thanks.
right. All right. Thank you. And I think this is the time to end the seminar. So thank you very much, Nick, for a nice talk.
Yeah, thanks again.
Thank you, Nick, for a really nice talk.